Ladies and gentlemen, I'm Kamil Witecki. I'm very happy to see you all here today. Today we are going to talk about testing and timeouts in tests and how to deal with them, how to tackle that problem. The session will take about 50 minutes, and after that we'll have time for questions and answers. So in case you have any questions, something comes to your mind, just be patient, we'll have time to answer your question. And maybe during the presentation I will just provide an answer to you and you can benefit even without actually asking the question. So what we are going to talk about today is how to turn this idle time in our tests into actually productive time and shorten the time span of our test execution. So how to ensure that we get results as fast as possible. This kind of gaps are caused by timeouts, and we are going to get rid of these timeouts. But I made some assumptions about you when making this presentation, and now I would like to verify these assumptions, so it's time for me and you to do some kind of exercise. So I would like to learn from you if you are actually using any kind of automated testing. If you do, please raise your hand. Okay, so my assumption was more or less correct. Most of you do. How many of you are dealing with timeouts in tests? Okay, more or less half of you. The other half may be dealing with them in future, so it's not in vain. I'm very happy that I will be providing something that you might be interested in. How many of you had the problem that your tests take too long because there are timeouts like 60 seconds because you just have piece of code that sends a message to remote server, waits for the response, and there is just this kind of security timeout that after 60 seconds will proceed either way. So how many of you have this kind of security valves? Okay, more or less 1/3 of you. So yes, we are in the right room. But before we'll jump into this, I would like to share with you a story. So I would like to tell you where this all started. So a few years ago, I was part of the project, I was part of the decision team, and we were just about to deliver the project. But we had this one nasty rule, this quality rule. Nobody likes them, but they are very important actually. So we had to ensure that the software passes 120 hours of stability run. The stability run is very simple thing. You just load the software into the system, load it with a lot of users, a lot of transactions, and so on, and just wait a few days, see if it didn't crash. The problem is, during that time, something went wrong. When you are looking at that diagram, it's not very obvious, but if we zoom in, yeah, there is a problem. There is a memory leak in that software. We cannot release it. But the deadline is coming closer and closer. And 120 hours is 120 hours. So what to do? So we're starting to discuss with all the decision team, and there are different ideas. Like we can reschedule our tests, we can run tests in parallel, we can start stability run, skipping unit tests, all these kind of ideas. And there was this one guy. He just stared me into my eyes and asks, "Hey, Kamil, what do you think? Can we squeeze 120 hours of testing in 72 hours? What did you just say? It's incomprehensible. But what we are going to do today is exactly that. We will try to squeeze this 120 hours of testing into 72 hours. We can do that, but there are some conditions. So to do that, we will need to, first of all, ponder upon what time is and why do we use timeouts in the software. We will need to model our software around some kind of work-oriented model. We will choose event loop and event processing queue just to be sure that all the valuable work was already done. And last but not least, we'll need some capacity that we can turn into shorter schedule. So obviously, overall schedule is CPU limited. In what I'm going to show you, there is no magic. It's not like we would make the overall schedule shorter in general. We'll just make sure that these gaps are filled with the work that would have been done later on. So If you count CPU cycles spent on your testing, it will be more or less the same. It might even be a little bit higher. But if you consider overall schedule latency, this is where you will benefit a lot. So considering that not all software on world is having huge gaps here, some tests of yours will already be like that. So you might have optimized your timeouts in tests just for testing purposes so that they expire exactly at precise moments when you want them to expire. So you have some kind of fine-tuned them just to make sure tests are fast. But then, if you do that and you would get slower CPU and run this kind of tests, that it will turn out that the CPU took a little bit longer to execute your tests, and the timeouts will start to expire too early, and the tests will be compromised with false positive values, false positive results. So another benefit of using this kind of framework is the fact that our tests will be way more reliable. So consider this simple example. We have here a state chart that is showing us some kind of supervision mechanism. So there are two states, connected and disconnected. There is some device behind that state machine, and that state machine is just checking if the device is there. It's sending ping request and pong request. And if it receives an answer, it means the device is there. If it doesn't receive an answer and the timeout expires, then obviously the device got disconnected and we need to reconnect to it. So now I would like to test if this state machine was implemented correctly. And if it says in specification that this timeout should be 30 seconds, I would like to check in a black box way if it's really 30 seconds. I wouldn't like to just peek inside the code and see, yeah, it says 30 seconds, check. No, I want to automate my test and I want it black box so that it's part of my CI loop. And how do I do that? No idea really. If I am not using this kind of framework, I could have reverted to some kind of probabilistic testing. So just send 100 events around this 30 seconds boundary and see if half of them took one path and half of them took another, then probably everything is correct. But this leaves us open to false positive results. And if there is anything that I don't like more than very long testing cycle, is false positive or false negative results. I hope you are on the same page with me here. So before we'll go into details how to implement that, we'll see what is really happening underneath inside the application. We have this example, very simple one. It's even simplistic. But you have here 3 timeouts. 2 of them are dependent. 2 of them are changing the state of the application. And the third of them set far in the future. 1 second in future in terms of CPU is eternity. That is basically verifying the state. Obviously, if you are running it on any decent CPU today, it will always pass. But it will take 1 second to execute this example. So we wouldn't like to wait 1 second just to check if this state was changed to Pong in the end. It's the amount of CPU cycles this code takes can be measured in nanoseconds. It wouldn't probably even reach 1 millisecond on its own. So we are wasting 1 second to get that result. In case of big application, it would scale. And that scaling factor would be really prohibitive when it comes to feedback loop. And now, very naive approach to solving this problem, very naive approach to make the whole testing time faster would be to just intercept the timeout setting method and divide our timeout by 1000. So 100 millisecond would become 0.1 and 1 second or 1000 milliseconds would just become 1 millisecond. So getting result in 1 millisecond is something that I can settle for. Just a question, how many of you think that this will actually work? If you think that this would work, just raise your hand. Okay, I see no hands, so you already probably tried this kind of stuff and it didn't work for you either. Very well. It would be worse if it actually would work for you, because it would give you false impression that this is a good solution, but it's not. What happens is our code fails when we are using this kind of patch. Now let's see inside the application why it fails. So we will have this simple model. We'll have queue of timeouts, queue of events, some kind of time scale, and the internal state of the application that will be changing to ping and pong. And afterwards, it will either turn green or red, depending on the moment when it was verified, and if the state was correct during that time. So first, we'll see how it works in case of proper execution. So we execute the main script. 100 millisecond event and 1000 milliseconds events are added to the queue. This one expires. It's adding another event to the queue, another timeout to the queue. It expires. The state changed to Pong. And now we are waiting a lot of time for this one to actually expire. And this break is on purpose, for you to feel how the CPU feels like when it's waiting for timeout to expire. Okay, let's stop it here. Now we will see what happens if we have sped up timeouts, if we have just cut them by 1000. So this happens. We have main event. The two events will be scheduled here, but the problem is they are expiring precisely at the same moment. And the state was verified already now, even this event was added to the queue later on. What happened? Internally, when we are talking about time, we are actually not having continuous time inside of the application. There must be some kind of granularity. Either it will be 10 milliseconds or 100 milliseconds, but there will be some kind of resolution. In the moment when we have just divided the timeouts by 1000, the two first timeouts got scheduled in the very same time window. So due to this resolution, we have cut the timeouts so much that they were no longer distinct timers. They got expired at the very same moment. And since the timer that would have changed state of the application to the proper one was scheduled only by one of the events, by one of the prior timers, the order of execution was broken. So we have introduced a race condition to our application. And this is what we need to really avoid. So the takeout from this short experiment is that speeding up time doesn't really speed how fast work is done. So if my CPU takes 100 milliseconds to execute some work, no matter how much I will divide this timer, the CPU will still take 100 milliseconds, and I cannot skip that. I just cannot speed up that work. I do not have faster and faster CPU. I can get twice much faster CPU, but it still will take 50 milliseconds then. So this limits us how much we can actually divide our timers. Second thing is timer resolution is also finite. So there will be something ticking periodically every 10 milliseconds or every 100 milliseconds, and just dividing our time into separate time boxes. And then, no matter what are our actual due times, when we have this kind of resolution, everything that falls into the same box, into the same time period, is indistinguishable. These timers will expire together. So let's look at that example from a little bit different perspective. We'll now look at it not as an event queue and event loop. We'll see it as a acyclic graph of events. So we have here main event that is scheduling two timers. One to expire after 100 milliseconds and one to expire after a second. So black ones are timeouts, white ones are events to be executed. Gray ones will be the ones that are actually changing the state of application. So obviously, first, 100 millisecond events should expire. It will change the state of application to pink and schedule another timer. Then this one should expire and change the state to Pong, what is the state that we are actually expecting in the end. And then 1000 milliseconds timer will verify the application. There is a huge gap between them. What happens when we are spinning up time is we are messing with these boxes. These are the periods of time that were created by our ticking timer resolution. And as long as we are just cutting this timer a little bit, this is what happens. Everything is fine. The order of the events, the position is okay, but there is a moment when it gets broken. So what we can see here is that this event cannot ever be executed faster than this one ends execution. So no matter how much we divide this timer, it's always constrained by the end of this execution. But this one is not constrained by anything. So if we choose too big value, its timer will go down to 0. And if we have actual CPU, this will take some time to execute, so will this. So we need to take into account this one, so the amount of time, the latency that is generated by executing the actual work. What would help us here would be an infinitely fast CPU. If I would have an infinitely fast CPU, then it would mean that this work took no time to execute at all. So didn't it. So the overall time that was spent on executing the job was 0. And this constraint wouldn't ever exist. So it would always go to 0 as well. But we do not have infinitely fast CPUs, and probably will never have. That's why we'll need to simulate them. On the other hand, if we want our tests to be reliable, we cannot do that. Because the more closer these are getting, the more error-prone our application gets. So if there is any issue with scheduling, if there is some process that will take over CPU for a few milliseconds, then overall execution time of an event will take a little bit longer. So if I can fine-tune these timeouts so that they are perfectly aligned in time, so that I minimize the time, then if anything happens that will cause my CPU to take even slightly bit more time to execute the job, then overall schedule will be compromised again. If I would like to have reliable execution, I would have to do something opposite. I would have to make sure that these gaps are getting bigger and bigger, so that I can ensure that no matter how much time CPU takes to actually process this job, this one is always scheduled later. But wait a minute. I told you that we are going to speed up this execution, and that would actually break it. So we are not going to do that. Don't worry. But we will need to do something else. So first of all, we'll need to disconnect from the wall clock. Just forget about the wall clock. Timeouts are not really about wall clock in your tests. In an application, yes, they might be about wall clock. So the server might be far away. I might have calculated that it will take actually 60 seconds. But in tests, it doesn't matter. I hope you all mock all the external interfaces like the server. You mock the database and so on. I hope so, but I don't know. So are you really this committed to automated testing that you are mocking all of your external dependencies? Raise your hand if you are really mocking all your external dependencies. Okay, it's more or less 1/4 of you. If I do a presentation next year, I hope the amount of people who are actually mocking everything will be higher. So we need to disconnect from wall clock and just forget about the wall clock. Just forget there is any clock. To do that, we'll just intercept the timeouts and we'll put them into some kind of priority queue. So our timeout will expire after the set time, and the reference time will just keep track of the reference time. So if we have moved time to future, we'll just start at that point and move further. So we have disconnected from wall clock. But now there is nothing to actually expire our timers, to actually schedule them. We have forgotten about wall clock, but now we need something that will actually move the work forward. And to find what can help us to actually move the work forward, we need to think what kind of conditions we want our application to be in so that we can push the time forward. So what these three places have in common? I can tell even from that picture that I do not want this one to ever cross that line. or this one to go before it. I want these points to just make sure that any work that must have been done before that event was already done, and that no work from this component of the graph was ever started. So this part of these two components will only be started after I expire the timer. So I control that. I have already disconnected from wall clock. I have my priority queue, but nothing will actually take the timeout from the queue and push it to event queue. So I am safe. I will never execute this one unless I want it. But how to make sure that all that job was done before I can actually expire a timer? And this is why we are using event loop and event processing queue. We basically want our event queue to be empty. If we have mocked all our external interfaces, if we have no external dependencies, then it simply means that nothing can schedule any work if there is no any work ongoing right now. So even if I have some kind of mock of a server, then if there is any work for that server to be done, there will be an event on a queue. If the queue is empty, it means all the work has been already completed. If you wouldn't have mocked all the external dependencies, then you could have received a message from remote server. So this would break our assumption. That's why it's very important to have all the dependencies mocked. But if we do, we can rely on the fact that if this queue is ever drained, if it's empty, then it means that either our application finished its job totally and we can just exit, or we can just go to another timer. We can expire just first timer on our priority queue and be safe, because there is no valuable work anymore for that application to do. And this is more or less what, for example, Node.js or Loovit does. So it monitors its internal event queue and all the callbacks that you have set, and if it sees that there are no events, and if it sees that there are no more waiting callbacks, it simply exits the application. So they are making the very same assumption that we are going to leverage here. Now, to actually benefit from it, we need to be able first to tell if the event queue got empty, and we can check it either from separate thread, but it will be possible just sometimes. Sometimes we'll not be able to spawn separate thread. For example, if we're using proprietary solution that is not thread safe, then we'll not be able to do that. Or sometimes we just have no control whatsoever over the application, like in case of Node.js or Loovit. And then we'll need to somehow force the queue, force the event processing loop to check itself. And another important question is how to tell if queue is already empty. How to tell if it got drained. Some implementations will provide you with method function that will simply tell you that. So you can just ask, is it empty or what's its size? But what to do when you have no chance of just simply interrogating the loop, interrogating the queue? If you do not have this kind of chance, you need to ensure somehow that the queue got drained. You need to drain it yourself. And now we'll just see different options how to implement this kind of model, this kind of framework in different situations. So first is the simplest example. We'll basically have separate thread. We'll be able to check the event queue. We'll define a new thread that is a forwarder. The forwarder will be simply checking now if the event queue is empty, if the timeouts queue is empty. If so, then our application is done. We can just exit. There are no events, there are no timeouts. It means nothing can happen in that application anymore. But if there are some timeouts, it will just pop one timeout and push it back to the event queue. Just one timeout. We cannot push more, just very precise one. We are cutting the time into pieces. So we are ripping time-space continuum here, and we are just telling that this part of time we already forgot. We have moved to this precise moment, and anything in the future, we don't care about it yet. And we just let application go. It does its job. There is some sleep, so that will not just busy wait here. It can be done in a way, but it can be done way better. So we can synchronize event loop and this forwarder, but it's not really necessary for this example. This will introduce some latency. It will be 50 milliseconds, but that's not really much in that case. If you need to go lower, you're always welcome to go. But there is a problem in this case. So one thing is that you must have access to separate thread, and it's not always possible. And another issue that you might get struck by, not necessarily, but you might, is this kind of event loop processor. So this event loop processor does one nasty thing that breaks your assumption. So it first pops the event from the event queue, and only then it dispatches it. So between these 2 points, the event queue is empty, but there is actually some work to do. And it can happen that our forwarder would have noticed, okay, event queue is empty, so I am pushing another timer there, but that would be a disaster because this event is going to be executed now, and it can schedule more work. So in that case, we just cannot use this kind of solution. It's valuable if you can. Keep it in mind, it's probably the most simple, but sometimes we just need to use heavier machinery. Now, a heavier machinery will be to force the event queue itself to check its state from inside of the event processing loop. To do that, we'll introduce so-called guard event. And our guard event will be the one checking the state of the queue. So now, no matter what the queue does, whenever it's empty, it means that there is just one event being processed right now. And if I am executing this code, I am sure that I am executing it myself. So if I am executing myself, I can make assumption that nothing will actually be pushed on the queue anymore. So I am checking that the queue is empty. If it is, I am myself forcing the loop to just take one timeout and push it to itself. So this way, I can implement it even if I cannot spawn another thread, or if doing it from another thread would be too risky and would expose me to race condition. This was the simpler part. So here we had this nice empty method. And this empty method told us if the queue is empty. But what to do if we do not have this kind of method? So this will be a little bit trickier, but not much. We'll introduce another type of guard event, but this time this guard will be a little bit fancier. So this guard will no longer execute this code because it can't. It cannot just check if the queue is empty. Instead, it will try to force the queue to get empty. So it will somehow may ensure that the event queue was run so many times that no matter how many events there were, if the size of our directed acyclic graph is finite, then the queue gets drained. So we'll have this kind of simple example. We'll have the directed acyclic graph, a little bit more complicated than before, but not much. And what we can see here is that we have some event, it's in black, and this event is the event that is currently executed. The white events are the ones that were not discovered yet. And there will be gray events that will be getting added to the queue. So gray events are discovered ones, already scheduled, but not executed yet. Black event is the one currently being executed, and white events are the ones that were not discovered yet, so we don't know if they will be pushed or not. In this example, we will push all of these events, so there are no conditions, but normally there could be. So we are executing event 1, and it's already on the event queue. Now we are adding 3 events to our event queue, and this one finishes execution. What we can see here is that we are always going breadth first. We are visiting these events in a breadth first approach. So if I do it breadth first, it means that these 3 events will always be executed before any of this, because I have already scheduled them. And now when I will start executing this event, I will add this one to the queue, but it will always land at the end. So I can somehow tell that I have cut this graph in layers. So the further from root there are, the bigger layer number they have. So the depth of the graph somehow tells me how many cycles this loop will do. And we'll try to leverage that knowledge to overcome the situation where we do not know if the event queue is empty. So I have now these 3 events here. I have cut it into that layer, and now I will execute these 3 events. And what happens is that this one's got gray, this got scheduled, and this one is here. So I am executing another layer now. And again, I will execute these 3 events. These 3 from another layer will be scheduled, but they will never be executed before all events from that layer were executed. So now it is very important to realize that this graph must be finite, and that's easy. We cannot represent really infinite graphs because we do not have infinite amount of RAM. But what's important is that they must never be cycles in that graph. If I would have cycle, then I couldn't have told you that there are some layers in that graph, because at some point I would just jump from here to here and I would break the whole assumption. But how many of you have ever written code that does recursion, but the recursion never ends? Have you ever done something like that? So the function just calls itself again and again without any guard. Did you? Raise your hand if you did. Yeah, almost everybody did this kind of a mistake. But it's nothing more than a mistake. It's the same in that case. If there would be any cycle, it's more or less the same thing as if there would be unprotected recursion. So I would be scheduling all the time the same events. The application wouldn't do any productive. So there would be no end condition. It means that it will just stall forever. So in real world, the events are really directed acyclic graph. There are no cycles and they are finite. So we can make an assumption that this graph can be cut in this kind of layers. So knowing that, we will introduce another guard event. This time it will not check if the event queue is empty. This time our guard will simply debounce itself from the queue. So it will get scheduled at the very beginning of the event queue. It will check if it already bounced from the queue, if it already did full cycle, let's say 500 times. And if it didn't, it will just schedule itself at the end. So after each layer, it will be pushed to the beginning. It will check if it was scheduled already 500 times, and if not, it will be pushed to the end again. So if I have 500 layers, it would be scheduled 500 times, and it will every time drain a layer. So it goes to the very beginning. It checks if it was already bounced from the queue 500 times. If not, it goes to the end. It's scheduled after all the events from that layer were scheduled. All the events from that layer are executed. It goes to the beginning. It checks if it was executed 500 times. If not, again and again. So with every cycle, it drains another layer. So in some cases, in some applications, you will be able to tell beforehand how many layers your graph has. But usually you wouldn't be. Usually the application is so big that you just don't want to know how big this directed acyclic graph is. But I can tell you that 500 layers of this kind is already way too much. We are testing actual software running in an embedded device, doing quite massive job with a lot of promises, a lot of asynchronous events that was doing fine with just 100 as the debounce number. So 500 will keep you safe, and in case it doesn't work for you, just increase the number. Debouncing this event in a queue 500 times will waste some time of a CPU, but it will be measured in nanoseconds or maybe 1 millisecond. So this is negligible compared to how much time we can really save on that. So yes, we'll generate a little bit more of heat, but we'll squeeze the execution time a lot. Now let's see this very same example of directed acyclic graph, but this time we will introduce our event to the queue. So it's green here. And we can see that the event from the first layer is scheduled here. And now we will be having also our guard. So we are executing this event. The 3 events got scheduled, but this one was moved to the beginning, and now it's going to the end. So it wraps the queue. It guards the queue, basically. And now these 3 events will be executed one after another. And again, the guard event is at the very beginning. It drained first layer, and now it guards another layer. And so on. It drains another layer, and it can check that it didn't yet bounce 500 times, and now it will just bounce itself from that queue another 495 times, but it's fine. It will take just a little amount of time. If you know that your application is simple, you can just change the bounce limit to 4 in that case, because we have 4 layers, and it would work as well. So this way, we were not checking if the queue is empty, but we were forcing it to get empty. Our event was just going in cycles one after another to ensure that the queue gets empty in the end. So it was draining it in one way or another. It was ensuring that no matter what could have happened inside of the application, we have reached a state when the queue must be empty. Now, do you remember, I guess you do remember the example from the beginning. We had this very simple piece of code. There is this first timer that does nothing more than just change the state of application and set the second timer. And then we have the third timer that is supposed to validate the state of the application. So our first very naive approach that we did was to try just to cut the due time of timer. And it didn't work. It was naive. It might have worked by a mistake, by a chance. But fortunately for us, it didn't. And this solution, if we want it to be correct, we need to disconnect from the wall clock. So just take all of our timers, put them into priority queue, and implement this kind of guard in one way or another. In that case, this guard will look like that. So I will set immediate, and set immediate is always set at the end of the queue. So if I have Node.js, if I have Loveit, I will always set immediate at the end of the queue. So there were some events executed. They have put all the events on the queue, and I am setting immediate at the end of the queue. And then I will be simply checking if the value that I am expecting was drained down to 0. If not, I will again set immediate at the end of the queue. This is actually the guard that I would implement for Loveit. In the case of Node.js, it would look more or less the same, but the syntax would be JS and there would be no timer here. Now, what I am doing in my application code, after I started running it, I am starting to I'm actually pushing this event to the queue, telling it should debounce 500 times. And then when 500 times already passed, I am just pushing this very simple function. So if I have already drained the queue, check if there are timeouts, and if there are timeouts, just execute one. And now if I run my code, this very simple example, with that kind of timer, with that kind of patch, everything works fine, and the real execution time is 10 times faster. So no matter I had this 1 second timer, it's now 10 times faster. And what is more, if I take just the Loveit, just the execution engine, and I ask it to execute print x from the command line, it takes not much less. So just evaluating this part of code here takes 100 milliseconds. So this probably takes more or less 100 milliseconds. So actual execution time got about 9 milliseconds. So this is a speed up that I am happy with. I hope you will be happy about this as well. Now, the good news is that here we have seen concepts and ideas. So you already know more or less how to implement it. So if you have any proprietary solution, you got here ideas, you got the concepts that will help you to implement this kind of solution for yourself. But the good news for those of you who are using Node.js is that there is already somebody who took care about you, implemented this kind of concept, and published his library on GitHub. So if you are keen on having a deep look into implementation of this kind of concept of a library that does exactly that, make sure you go to GitHub and you check out the Zurvan library by Tomasz Lewowski. This library will let you to start using it or understand better how these concepts work in practice. So, summarizing the talk, what we did was we took the right model for our work, where we can actually monitor how much work was done and how much work is there to do. This model is simple event loop and event queue, something that actual systems existing on the world are based on. Node.js is one example, Loveit is another example that you can simply use. There is plethora of different solutions also available for C++ and other languages. Second thing that we did was to disconnect from the wall clock. So we have somehow forgotten in our test that the timeouts are anyhow connected to the clock. We have tied them to the execution of the application now. And we have tied them to the fact if there is any valuable work to do or there is no more valuable work to do. So basically what we did was to mock the clock. So it's no longer the clock from the wall, now we are owning it. As we would mock our database, we have mocked the clock now. And last but not least, and probably the most important part, we have turned the idle time of our CPU into something productive, effectively speeding up actual execution. So now, when we are executing our tests, we'll get the results faster. It won't be always 10 times faster or 100 times faster, but if it's few times faster, we have already won a lot. The faster our feedback loop, the faster our feedback cycle, the more efficient we are as developers. So the sooner I know if the code I wrote didn't break anything, the sooner I can start working with something else. And if I can use something like that to just forget about issues that timers are introducing to make the execution time longer, I should do that. And I really encourage you to use this kind of solution, either in a form of Zurvan that you can use right now, or you can implement your own solution using the ideas we have just seen during the presentation. That's all I wanted to tell you. That's all we had for today. We are having still 15 minutes, and it's time for questions and answers. Thank you very much for your attention. If you have any questions, that's time for you.
Any questions?
Okay, I have heard. How did the story of the memory leak end? Did I get it right? Yes, so it's we didn't do that yet during that time, so we didn't squeeze the time magically. The story ended that we actually had a correction very fast, after more or less 1 day. And we were just lucky, and the stability run that we started next day passed. That's it.
Can you share the link URL on the GitHub? Because I don't see it.
I do not have it in the presentation, unfortunately. I will make sure that the version that will be presented on CodeDive webpage will already contain the link. So I will update it, and it will be there.
Good question. Can you get back to the place where you had debounce 500?
Sure. Would you like the implementation of an event in C++?
Yeah, because
yes.
I have the problem understanding if it's not conceptually the same as having a for loop with 500 iteration of push and pop.
Let me see.
Because you don't have any synchronization, you just push, if there's empty queue, you push empty event. So you just take the whole processor to...
Yes. In case there is no job to do, I will 500 times just push the empty event into the queue just to drain it. So this is a trade-off. In that case, if I know that the typical size, the maximum size of the graph would have 10 layers, I should have changed this value to 10 or 11.
Yeah, but I mean, can we just get the for loop with 500, going from 1 to 500, and it will do the same job?
It wouldn't, because what's important here is that we are taking this very event, pushing it to the queue, and it's only executed after the queue processed all the events that are there. So if I would have any other means of synchronizing the for loop with the fact that that some part of the job was already done, then I could. So I could have a for loop with this kind of event that would synchronize it all over some kind of mutex or conditional variable. Then it's fine. But what's important here is that this event is pushed first to the beginning of the queue, then it goes to the end, and the next execution is precisely after this whole layer of events is drained.
Would it be a reasonable optimization or simplification to just remember that we've executed 2 guards in one by one, and that would be the end of the program instead of this 500?
Yes, of course, it could be so.
Okay, thanks.
You're welcome. But then, adding to that question, in some cases you will not be able to tell if you executed 1 or 2 events, because if it's proprietary solution or closed loop like in Node.js, you have no idea if there was anything scheduled. So you would either mock all the methods that are scheduling something to the queue, or you would have to somehow ensure that there was nothing else pushed to the queue. So you could have mocked the push method to the queue, and then check what gets pushed. But sometimes you cannot just do that. But yeah, that's valid optimization.
You had some initial requirements about the stability of the application, that this test should run for a very long time. How do you know, after squeezing the time, that 72 hours of running the test meets the initial requirement?
I don't really know that, but I can easily verify that. So at the start of the application, I would have scheduled a timeout that must happen after 120 hours. And then I will simply start it with this kind of patch and wait for that very event that is scheduled after 120 hours to expire. If it expired, it means that amount of work done is worth 120 hours.
Thanks.
You're welcome.
So, Kamil, many thanks for your interesting presentation.
Thank you very much for your attention.